No, sorry, I didn't make it to finish them. I will definitely have it on Wednesday. I graded most of the problems. Most likely the average will be lower than last time. Again. That is probably a good response for you. In the top, you can see the
That's good, because that's super slow, isn't it?
Okay.
It's pretty slow, but it has a...
No, sorry, I was out of town this weekend. I didn't have a chance to hear it.
One-handed heavy attack and your...
Any other questions?
One-handed...
Just in the way things come up,
Are sweeps.
next week, we have class today. Certainly it'll be a full lecture. Class on Thursday will probably be mostly a full lecture. Monday will be somewhat of a review, though we may have to touch on a few things. There will be a homework 11, and that will be due on Wednesday. And it's kind of an extra credit homework. It's a comprehensive homework. It will replace one of your previous homework grades. Wednesday lab next week.
Yeah.
Losing track of days. May 7th. No lab. So the lab that we have on Wednesday this week will be the last lab. On that note, you can come in and work on homework 11 if you're so inclined. And I'll be there to help should you desire.
Is that one we're going to sign on that one? Or no?
Yeah. So homework 11 will be due Wednesday, May 7th. Right.
Oh, okay.
So you can't at any time. Okay. We're reaching the end of the semester. The final is a big deal. The final is comprehensive. We do have our due date, or our final date. I don't remember what that is. But what is it? The 13th?
15th.
So it's not quite the last day of finals week?
Second block.
16th is a Friday.
Friday's the last day? Well, if you treat this week's homework as due on Thursday, you'll be done with it. So whoever said 2 homeworks due next week. There's no reason you don't have to finish the homework by Thursday. All right. So back to more interesting topics. Well, puzzles is fun, but the T model for mutual inductance. So in general, what we're looking at is a source. And to be a little bit general, we have a source impedance, and we can write it as ZS. Yes, usually our source impedance is resistive. There's some passive values there, but it could be capacitive or inductive as well. And then we have an inductor in L1, and then another inductor in L2, and then a load impedance. And ultimately, everything can be set up like this. So maybe ZS and ZL are more complicated, and even if you want, you can call DS B Thevenin, but eventually we can reduce everything to this form, some Thevenin circuit with some coupling with a load. And so that's not something we haven't seen before. There was a lot of negatives in that sense. And so between these, we have coupling between L1 and L2. And that's the mutual inductance. And that's M. And that has units Henrys. So effectively, it is another inductor in some sense. So it's a model inductor. The real effect here is from the magnetic field coupling. And here's our relationship between L1 and L2 right now, where K is the coupling coefficient. And K is bounded between K, or between 0 and 1. No coupling. Complete coupling. Completely coupled. No negative numbers here or anything like that. And so K is an artifact of the materials that's forcing the coupling. In the case of a transformer, it's very large. In the case of air coupling, it's usually very small, but can be significant. And in some sense, this is a parasitic effect as well. So you have two wires running side by side. There is a mutual inductance between them. It can be significant, but one thing we haven't talked about, and you'll see it a little bit in Introduction to Electronics, is the more dominant effect here, when we look at things like this, is parasitic capacitance. And so we're looking at the T model for mutual inductance. It has bearing on transformers. It has bearing on parasitics. But when we start to talk about parasitics, capacitance is usually the bigger factor. So, what are we doing here? Well, this L1 and L2, like we drew last class, just to draw that again. There's L1, there's L2, and there's a K in between them that's coupling them together. And equivalently, M again equals K square root of L1 times L2. Our T model looks like this. And we did this last class. And there's our equivalent circuit. And what we're looking at here, and this V1 and V2 are somewhat arbitrarily chosen, though we did use them in transformers as well. The voltage across that and the voltage across that better be these equivalent nodes. Or these same nodes, I should be a little specific. And so that's what we're doing, is we're taking that separated K, L1, L2, and creating a circuit model that we can use in PSPICE. I mean, this is something we can analyze. We can analyze it by hand if we're so inclined, or PSPICE if we're feeling lazy, which is usually the better choice. And so that's all we do. Once we replace this transformer, or this mutual inductance circuit, with the T model, it becomes a phasor problem, or an AC steady state problem, if you want to say it like that. So ultimately what we're doing here is we just take this circuit, and we can redraw this circuit as something that looks like this. There's the V source. There's L1 minus M. There's M. L2 minus M. And Z load. And there's our equivalent circuit. And so again, whatever ZS and Z load are, we can plug those in, we can analyze this. So we have done circuits this complex before. Maybe it's not very fun to do by hand because it has a lot of algebra, but it's a fairly straightforward analysis. And looking at this, the voltage here, which we just called V1, and the voltage there we call V2, we recognize that V2 is the voltage across the load. And so if we do whatever AC steady state analysis on this, we can find the load voltage. And we can look at that for just a second. And since I don't want to really write things out all over again, in general, we could do this by hand. So how would we analyze this circuit to find the load voltage? Well, we call that VA. We could do a voltage divider. Effectively, at some omega, this is ZM. This is ZL1 minus M. And this is ZL2 minus M. Those L1 minus M's are subscripts. And so, once we know omega, those just become complex numbers. J omega times whatever number this happens to be. And so, well, in that form, we can analyze this using Z's. We can write VA equals, well, Zm with these in series, so Zm in parallel with ZL2 minus M plus ZL, right? These two in series in parallel with that, all over Z source plus ZL1 minus M plus those things in parallel. We should recognize that. Now again, I'll agree that the algebra after this, not so pretty, but we can write that down fairly quickly. So that's a fairly straightforward derivation. And then we can write down now VZL. Well, that's just the voltage divider relative to VA. And so ZL over ZL plus ZL2 minus M. Oh, and all this times V source. And times VA. And then a substitution in there, and now we have VL relative to V source. And we can use that. I mean, if we want to do this, plugging in numbers for phasors, we can do that, find out what all our equivalent circuits are, and check the voltage across the coupled, in this case, load impedance, but whatever you want to call that. And so, fairly straightforward. Once we get in this form, nothing new has been brought into the situation. So the only trick, the only magic we've done here was take this circuit and redraw it as this. And after we've done that, everything we do is something we've done before. Now, it is worth using to study a few of our cases. So if we think about our transformer, in this case, we can say K equals 1 or close. So we have totally coupled, completely coupled inductors, but finite inductors. So maybe I can put real transformer in here. Completely coupled. L1 and L2. But finite. L1 and L2. And so it's an ideal transformer in the sense that they're totally coupled, which is not unreasonable and really good materials. K very, very close to 1 is okay. But L1 and L2 are finite. Why does that matter for us? Well, if we think about this circuit, if that's 50 ohms, let's make this a little bit easier. Let's make it 1K. Well, if this is 1-to-1, and this is some V source, then V load equals what? In an ideal transformer, what's V load?
Yes.
Yeah.
Not quite. It's 1K and 1K. Well, if we refer the secondary to the primary, what's the referral? What's ZL equivalent?
1/2 V.
Yeah. So VL equals V source over 2. Right? Seems reasonable. Well, let's look at our circuit. Let's use, I don't know, let's make things silly. So there's our 1-to-1 transformer, and K equals 1. So M equals 1 times square root of 1 times 1. And sure enough, that's 1. Big mystery there. Well, what does our T model become? Well, if we draw that out. So we have V source. That's 1K. And L1 minus M, in this case, is 1 minus 1 equals 0. Is that a problem? What's an inductance of 0? Yeah, it's a short. So it's equivalent to 0 resistance. It's a short. And now we have an inductance of 1 here. M equals 1. And similarly, L2 minus M equals 1 minus 1, which is 0. And we have our 1K there. So there's our T model for our real transformer with inductors of 1 in this case. And 1 is a big inductor, but not an unreasonable value. It's not out of the question. And so just to draw that one more time, this is what we're looking at. And I haven't done anything with frequency yet. This is a phasor problem, or an AC steady dose. That's a resistor. An AC steady state problem. And so looking at that, well, what's the condition for this to act like our ideal transformer? So if we think about this, this is ZM. There's our Z source, and there's our Z load. And our ZL1 minus M and our ZL2 minus M are 0, so we don't write those out. What's the condition then? When is the voltage across our load going to be 1/2 our source voltage, which is what it was for our ideal transformer?
Infinite frequency.
Well, we don't have to go quite to that limit. Let's be a little bit more general than that. So what condition do we need for this real transformer to act like the ideal transformer? Well, we already know K is 1. We have 2.
ZL much less than ZM.
Or more specifically, these are fixed. ZM much, much larger than ZL, than the real transformer, acts like an ideal transformer. And so, well, in this case, that means ZM is much, much greater than what? Well, if we write this out, and we should be a little careful, I tend to forget my magnitudes, but we're really talking about magnitude because ZM is imaginary and ZL is real, so we're comparing relative magnitudes. And so what does this imply? Well, this implies omega times 1, there's our inductance, is much, much greater than 1,000. And so in this particular case, the real transformer acts like an ideal transformer for frequencies, radial frequencies, much, much larger than 1,000. And we've talked about what much, much larger means. I mean, you can use a factor of 10 if you're so inclined. We've seen people use factors of 3, whatever, factors of 100. I mean, that's a sufficient description. Omega much, much larger than 1,000 for this problem. So what does it depend on? Well, when we consider real transformers to act like ideal transformers, what are our dependencies? We have 2. And what factors in here? There's 2 things that matter. One of them should be obvious. ZL. So as we change our load impedance, the range of our frequency is going to change. So if we were at 100 ohms here, well, then we could operate at a smaller frequency. What else matters? N. Yes, N, but
I think you said
no. Yeah. And M depends on what? Depends on the inductance. It depends on L1 and L2. So as our inductors become larger, so if we crank up our inductance, here we used 1 Henry inductors. What if we used 10 Henry inductors? How would that change it? Well, if this was a larger number, then we could go to a lower frequency. So as we increase inductance, then our frequency range at which our real transformer acts like a real transformer is larger. And likewise, it's dependent on the load. But the load can be anything, so really, as you look at transformers, you want these to be larger, which is why in the lab we had such big transformers. Those are designed to operate at 60 hertz for quite a variety of loads. And so they're big. They're, actually I can't remember what they are. I should have measured them before class, but reasonably big transformers. I should remember, I haven't measured them enough, but somewhere in the 100 millihenry range, I think. So, that's one of our criteria. And it's also one of the reasons why I had you start with a high frequency so you're well into the ideal transformer range, and then you drop that frequency in around 1 hertz or 10 hertz, you really start to notice the coupling tapers off. All right, if you remember from last week. And then there are a couple other goofy things going on, which actually I'm not completely sure why. I think it has something to do with the discovery board. So other things that we can look at: open circuited transformer, and compare it to the T model. And again, we can look at just the one-to-one. It's no problem. Excuse me. We call that 1K again. Well, if this is an open circuit transformer, what's the voltage across V1? So if it's an ideal transformer, V1 is what? Yes. You guys watching a good movie back there? Very intense. Is it the cat that got its head stuck in the fence?
What?
So what's our T model look like? Well, again, if we're looking at the one-to-one transformer with the same inductances we used before, here's our T model. And again, we have a short circuit here. And there's our open circuited load. Well, now this qualifies things once again. For our T model to be consistent with our ideal transformer, what must be true? So again, we're looking at, this is V1, this is V2. Well, in this case, I hope you agree V1 and V2 are the same. They're shorted, so there's no connection between V1 and V2. They have to be the same voltage. So that checks, since it's a one-to-one transformer. But we again have a limitation. What must be true for our T model to be consistent with our open circuit expectations of an ideal transformer? Something we just looked at a second ago, but this is the other side.
ZM much less than ZS.
The flip. So we want ZM much, much larger than ZS because they're in series now. So if we want the voltage across here to be here, well, that's true when the impedance of our mutual inductance is much larger than the impedance of our source. And again, so that's going to be frequency dependent. And likewise, we can do the short circuit. And that one's a little bit more straightforward. One, there's a ZS. In this case, our short circuit load, ZL equals 0. And our T model then And so here's D1, there's D2. In this particular case, what can we say about the short circuit model relative to ideal transformers? It always works. You short circuit the load on the transformer for complete coupling. There is no impedance dependence. This shorts out this, and the voltage goes to 0. Why didn't that work in the lab? Right, so I'm lying to you like I usually do. And so the real T model, the more complete T model, this isn't going to be on the test, so you don't have to panic. But it is worth knowing, and you'll see it in energy systems. So a little bit of a preview. The more complete T model includes resistance of the windings. I'm using RG there. That's resistance internal to eddy currents and the resistance of the domain switching as the magnetic field goes back and forth. So that would be a more complete model. It can get even more complicated, but you'll look at this in energy systems a little bit. And so as we look at this, well, things get a little bit more messy, but it is still just a phasor problem, yeah.
Why is the resistance of eddy currents when it's not in parallel with
Because you can still short it out. So there are other resistors in series. So it's a parallel effect. So if you get more complicated, you could add more windings here, more effects here, depending on what the appropriate substrate is. So these are all the different things we can do with the T model. To just look one more time, let's look at a different case. We look at the one-to-one. Let's look at a 1 to 2. In this case, let's again look at the short circuit test. Well, for a 1 to 2, what do we have? We can still have K close to 1, so it's a reasonable thing to say that the inductors are tightly coupled or completely coupled. To get 1 to 2, L1 says 1, L2 equals 4. So the winding ratio goes with the square of the ratio of inductances. Again, this is a little bit beyond the scope, but it's worth noting. And so in this case, m equals 2. Well, how does that play out for us? We think about it. There's our ZS, some finite value. Well, this is now 1 minus 2 equals minus 1 in terms of inductance. That's 2. And this is 4 minus 2 equals 2. there's our short circuit. Is that a reasonable circuit model? Can we have negative inductance in our circuit model? Sure. Just like with Thevenin circuits, where when we have dependent circuits, we can effectively build a negative resistor. It's a reasonable model. This is a model. These are not real components. This is a model. This is the real component. And so when we build something like this is an equivalent circuit, and negative inductance is okay in the equivalent circuit. If we pick values here, if we looked at a frequency, what plays out here? Well, meg equals 1,000, for example. And so there's some D source operating at 1,000. We'll make this guy 1K. And so what do we wind up with? Minus 1,000. 2,000. 2,000. And our short circuit. Well, coming back here for a second, again considering ideal transformers, for the short circuit load, what's the current through the source? What is the current through the source if we short circuit the load? What's the voltage here? Not a trick question. That's not a good answer. What's the voltage across the short? And if this is an ideal transformer, what's the voltage here? So if the voltage here is 0, what's the current through the source?
Yes, yes,
IS. IS equals VS over CS. In this case, 1K. Well, for it to be an equivalent circuit, again, we're emphasizing that concept. If this is going to be an accurately equivalent circuit, what does the voltage here have to be? Well, it better be the same. These are the same. We haven't changed this part of the circuit. If this is equivalent, it has to be the same. It has to play out the same. Does it? What's the impedance of that looking in? It's 0. 2 inductors, well, to write this with a little bit more rigor. J's in front of them. 2 impedances in parallel. We have those. J1000 minus J1000 equals 0. Does everyone agree? So there's our current. IS here still equals VS over ZS. That checks. And what about I load here? We've really done current as much, but in ideal inductors, what's I load for this ideal transformer? Well, this is 1 and 2. So what's the rule for inductors? The current here, make it more consistent. What's the inductor rule for an ideal transformer? I2 equals what? In terms of winding ratios and I1. IS over N. Do we agree? Should be half the current. Those were our 2 ideal inductor ratio relationships. V2 equals N times V1. I2 equals I1 over N. Right? Well, in this case, does that work? Here's I load. What's I load? You keep saying 0. What's I load? coming in here, which is VS over ZS, we can do this by inspection. I source coming in, we have two of the same impedances. What does I load have to be? IS over 2. Let's check. So our transformer model works, our equivalent circuit works, and they accurately model our transformers, at least in the cases we've studied. So that's the T model. Any questions on this before we dive in and do a team assignment? No? All right.
Great job. Yes.
T model should be good on the homework with regard to that. I like the transformer stuff. I think the T model is interesting, but as far as this closing unit, power I think is the significant part of this. You'll be re-exposed to transformers and the T model in more detail in energy systems, at least those of you who are EEs. So you'll see that in a lot more detail, a lot more complete derivation. Actually, this part of the class, I'd really like to spend more on power. So, power. We haven't talked about power for a while. And so, well, we have DC power, something we saw 14 weeks ago or so. Power equals voltage times current, or if we want, V squared over R, or if we want, I squared R. So that was DC power, no problems. Voltage times current, those are DC values, they're constants. We can multiply them out, we can get our units in watts. And it's all real power. Always real, which implies power is not always real, which is true. Well, if we look at the same type of setup, we could do something really, really trivial. If we have an AC source, V source, and a resistor, there's an R. And so, well, in this case, V source, some sinusoidal source, V naught, cosine omega t. So there's our AC source. And we can figure out what the current is by just applying Ohm's law. I source, I can write it a little bit generally. I naught cosine omega t. And by Ohm's law, we can say that's V naught over R, cosine omega t. No surprises there. Well, I'm going to contend that the circuit does also have real power. Resistors dissipate real power. So I'm going to just say power equals V source times I source. That is, in this case, both power consumed and power produced, depending on the sign. But, well, if we plug in here, things get a little bit more complicated. There's our V source. And there's our I source. Things are sinusoidal. And so, well, we can rewrite this as V naught I naught, which looks very familiar. It certainly has units watts. And cosine squared omega t. Right? And that becomes just trigonometry. So we can take advantage of some of our trigonometric identities, V naught, I naught. And that's 1 plus cosine 2 omega t over 2. It's just the cosine squared relationship. 1 plus cosine 2x over 2. And so we can rewrite this as V naught, I naught over 2. times 1 plus cosine 2 omega t. Well, if we plot this out, this is twice the frequency, of course. What does this look like? Here's our power, and here's our time. And we wind up with something that looks like this. Repeating. And those are supposed to be fairly periodic. That's the cosine squared function. And this has amplitude V naught, I naught, and then down here 0. Well, this is a special kind of power in some sense. This is instantaneous power. Or as a function of time. So we can ask what the power is at a given instant. And we've said it before, and I think it is a little bit, takes a little bit to grasp this, but these are sinusoidal sources. We're used to working with our phasors or our amplitudes or whatever the case may be, but these are oscillating sources. And at some point the source is 0, and at some point it's at its peak. Well, at whatever instant in time when the source is 0, the power dissipated is 0, and that's what we see here. You know, in this case, every half cycle, because this function's at twice the frequency, but every half cycle, our power goes to 0, and then every half cycle, our power reaches a peak. Is that interesting? Well, I guess in some strict sense, yeah, it's kind of interesting. But really, what do we care about? We don't care about instantaneous power. Power's oscillating all the time. But what do we want to know, in some sense? Do we really want this information? We want average power. There's our power average. Well, going back and looking at this, what's our average voltage? Not a trick question. It's the average voltage. Thank you. What's the average of a cosine? 0. Our average voltage is 0. So the average of a cosine or sine is 0. What's our average of this term? 0. So what's our average power? Power average, not 0. V naught, I naught, over 2. There's our power average, in this case, here we're fuzzy. The cosine term on average goes away, and we're left with the V naught, I naught times 1. So the average of 1 is 1, the average of cosine is 0. And so there's our average power. And we can rewrite this in lots of different ways. Once again, we could rewrite this as V naught, let's bring that 1/2 out front, V naught over R. Or we could substitute that, 1/2 I naught times R, I naught. And that all looks the same. No particularly different relationship with regard to the DC. On the other hand, we can rewrite this as V naught over square root of 2 times I naught over square root of 2. Right? That's the same thing. Hopefully we agree if we multiply those square root of 2's together, we get 2. And likewise down here, we can rewrite this as V naught over square root of 2. Bring that 1 over R out front. V naught over square root of 2. And here we can do that. R I naught over square root of 2 I naught over square root of 2. We notice this commonality here. The form very similar to our DC forms. V naught, recall, is amplitude. That's the amplitude of the sinusoid. For completeness, since we've used it in lab, V peak to peak equals 2 V naught. Peak to peak voltage. This one's not so important at the moment, but we've used it a lot and emphasized that it's there. Well, that V naught over square root of 2 also has a meaning. It's called the RMS voltage. RMS stands for root mean squared. Exactly. And so you've probably heard that term. And so, in effect, in a practical sense, in the question, what do I need to know to do well in the exam? V naught over square root of 2 is the RMS voltage. That's what you need to remember. And so, when we write this, well, looking at this P average for our AC signals, remember this is AC now, AC steady state. This winds up being VRMS, IRMS. And this winds up being 1 over R, VRMS squared. And this winds up being IRMS squared R. And that looks very, very familiar. And so this is the equivalence. This is the AC equivalence in power, so we can treat our power calculations the same way we do our DC power calculations. This is the average power delivered by an AC signal. Where does that square root of 2 come from? It's worth looking. What does the root mean square mean? Well, if we look at the voltage, again, V equals V naught cosine omega t. Well, root means take the square root. 1/2. The mean, if you remember from calculus, it's probably been a while. 0 to t, that's the mean. So it's the limits of integration divided by that length, or those limits. And then there's the mean, and then V naught cosine omega t squared dt. Square, mean, root. Which is over there. That's the root mean squared. And we can go through that math. It looks actually fairly familiar. 1 over t, and then roll 0 to t. V naught squared, cosine squared omega t, dt, so the 1/2. Well, the V naught's a constant as far as the integration goes. V naught squared over t, integral 0 to t. Again, we can apply trigonometry. Trigonometry, that sounds funny. Cosine 2 omega t over 2 dt to the 1/2. What's the integral of the cosine term over one period? 0. It's the average. So this winds up being V naught squared over t, integral 1/2, 0 to t, dt. Very complicated integral. Probably spent 2 weeks on it in calculus. V naught squared over t, t over 2, to the 1/2, and lo and behold, equals V RMS. That's where that comes from. So it's always nice when calculus plays out for us. And that's really the definition. That's the one thing you want to take away from here. We have these three kind of general references when we talk about AC signals. V naught is the amplitude, V peak to peak is twice the amplitude, and V RMS is the amplitude over square root of 2. That's the key thing to remember as far as a practical, how do I do this problem question goes. Where this comes from is certainly interesting and worth knowing, but these are the values we want to look at. Well, life is not always so easy to have resistive elements. If we generalize this, we have some V source, and we have some arbitrary impedance. And again, use our familiar ZL. Well, we still have I source. And so if we think about this, what's our power now? Well, our power across our load, well, it's in parallel with our source. So our load power winds up being V load, I load. And we're going to write that as V naught over square root of 2 times I naught over square root of 2. Nothing's changed there. And I need to be careful, sorry, I do this a lot. I want to use an S here. An S is the total complex power. Why do we need complex power? Well, if Z load equals a Z real plus a J Z imaginary, what can we say about the current and the voltage in the load?
They're out of phase.
They're out of phase. So there's a phase difference between current and voltage. What can we say about the current and voltage if our load is purely resistive? They're in phase. If current and voltage are in phase, then the power is totally real. If this was a capacitor, how much out of phase would they be? 90 degrees. So as we look at this, we can generalize this expression to be VRMS, angle VRMS, IRMS, angle IRMS, times the complex conjugate, or as a complex conjugate. That would be the full expression. So if we're going to do this in phasor form, we do a complex conjugate, which is equivalent to that trigonometric calculation we did just a moment ago. Why? Well, remember in a full sense, V equals a V naught, either J omega T plus phi v, and I equals some I naught e to the j omega t plus a phi I. Well, if we take the complex conjugate here, what happens to our omega t terms? Something we dismissed before, but they're always there in our phasor form. So e to the j omega t times e to the minus j omega t. And that winds up e naught I naught e to the j omega t plus phi v minus omega t minus phi v, phi I. And these guys cancel. I naught e to the j phi v minus phi I. Well, this is a specific thing. What's the angle of the voltage minus the angle of the current? Depends. Ohm's law is our friend, angle of impedance. So this winds up being the angle of the impedance. And that leads to all sorts of mathematical expressions we can use for power now using this complex conjugate concept. To write this out, just V angle V equals I angle I, just so we see it. These are magnitudes, the little magnitudes there. Magnitude of Z, angle of Z, and we recognize then angle of Z equals angle of V minus angle of I with a little rearranging. We have done phasors for a little while, perhaps, a couple weeks. Worth reminding. And so where does that leave us? Well, we have S complex power. AC steady state signals. And S equals V RMS times I RMS conjugate. In phasor form. V RMS, I RMS. Well, you can do it in rectangular form as well, but phasor form is always easier. Right? Our magnitudes multiply and our angles add. Or we could do some substitution in here. We get very similar relationships. VRMS is IRMS. Oops. Let's do it right. Times Z. Times IRMS conjugate. Well, what's IRMS times IRMS conjugate? That's the magnitude. That just winds up being IRMS squared times Z. Complex power, though, remember impedance can be complex. Depends what component we're looking at. And if we write this out just for completeness, well, what's IRMS squared in terms of amplitude? That's just I naught squared over 2 times Z. And we already wrote it like that once before. Just a quick substitution. IRMS is I naught over square root of 2. Square that, I naught squared over 2. And we get back to where we were just a few minutes ago. And alternatively, the RMS times the RMS over Z conjugate. Just substituting in for I. Ohm's law right there. And what do we have here? 1 over Z conjugate, VRMS times R times VRMS, VRMS squared. And again, we can substitute that in and say 1 over Z conjugate V naught squared over 2. And so these are all various ways of looking at the same thing. So no matter what we have, current, voltage, if we have 2 out of 3, or impedance, we can find the complex power. I call this complex power. Looking at these terms for a moment, real or complex? Real. Real or complex? Real or complex, it depends on the impedances, of course. So, this is real, this can be complex, this is real, this can be complex. Together, we'd have to look a little bit specifically there. What does that mean then? Well, I call this S. S equals P plus JQ. If we take this phasor form and convert it to rectangular form, so we can express S in phasor form or in rectangular form. In rectangular form, this is real power. This is imaginary power. Or more specifically, reactive power. That's the words you want to use to get into the good part. So imaginary power is reactive power. And this is complex power. Should have left room for units. Watts. Seen that before. Volt amps. Reactive. Bar. And volt amps. They all have the same units, but they're identified different ways. So total power is volt amps. Real power is in watts. And reactive power is volt amps, reactive, or VAR. And at this point, it just becomes complex math, something we did phasors at the start of Unit 3. Beyond this, there's no particular surprises, other than some qualifications. What must be true as we look at the power in the system? Something that we looked at back in Unit 1. Right. Power is conserved. So power produced has to be equal to power consumed. Well, as we think about power consumed, only real power does work. What is the reactive power doing? We've kind of brought it up before. I didn't quite hear you there. Well, if we think about a circuit of resonance, what happens in an RLC circuit of resonance? Are the voltage across the capacitor and the voltage across the inductor zero? No. Not zero. They sum to zero.
Equal and opposite.
but they're equal and opposite. So what are they doing with regard to power? They're trading it back and forth. So reactive power, in some sense, if we want to kind of generalize it, use it a little bit slang here, it's thrown back and forth between components. And the components can include the source. During half the cycle, and then it discharges back to the source another half the cycle. So it throws its energy back to that source. So it's just going back and forth, but not doing any real work for us. So only real power gets converted to heat or mechanical energy, as the case may be. But complex power must be produced. So in some sense, what do we want our Q to be? What do we want this reactive power to be? That's a goal. Ideally, 0. Why? Well, more, you have to pay to produce. So if we think, we go back in time a long ways. We consider our DC situation again. RS, RL. For a given RS, what is power across RL max or less? Remember? It's been about 14 weeks. When do we maximize power across a load for a given?
When RL operates.
So if RL's is short, how much power across RL? Power, if RL's open, how much power across RL? Is it 0 all the way? I just let it cool. What's that one? So for a given source resistance, you maximize power RL when it's the equivalent resistance. Now ideally, we can maximize power to RL as this goes to 0. We move that peak closer and closer, and if this becomes 0, we get a nice asymptote, and we can provide infinite power to RL by shorting out RL. What is RL? That's your house. If we connect every house in parallel, what's the effective impedance of all our houses? Small. So as we connect more and more houses in parallel, we can shift this. And that's arguably maybe one goal of the smart grid, though that's really not specifically one of them. But one of the goals actually is to make RS close to 0. Well, this was DC. There was a push to actually supply DC power. Anybody read about that? There was I can't remember who it was. It was a story I should remember. When we were first modernizing cities and laying power lines, There was a strong fight to have DC versus AC. Anybody know why AC won?
Usually transport.
Yeah, it's for longer transport lines. The resistance of the lines was too significant for AC, whereas AC power is between the lines, so they have less loss. And I should remember who was in that battle, and I can't. Yeah, Edison was one of them, but I can't remember who he was. I don't know if it was Tesla or not. Was it? Okay. Tesla was responsible for so many crazy things, but anybody read about Tesla?
He's crazy.
He was insane. He was brilliant but insane. So we have a ZS and a Z load. And our ZS equals a ZS real plus J ZS imaginary. We have a fixed source. And Z load equals Z load real plus J Z load imaginary. If we think about this, what's the current produced by the source? Well, IS equals VS. These are in series. ZS real plus J ZS imaginary plus ZL real plus J ZL imaginary. Well, to maximize power effectively, what do we want to do? We want to maximize current. How can we maximize current here? Ignoring these guys, what can we do with these guys to maximize current?
Increase frequency.
So if ZSI equals minus ZLI, they're equal and opposite, and what do? They cancel out, and we wind up with ZSR and ZLR. And so our goal to maximize, and this is a little bit messier to prove with derivatives just because it has complex numbers in it, maximize power to load. ZL equals ZS conjugate. So our imaginary components are equal and opposite. So these are things that we look at. And this actually is one of the active things that's really is trying to be done. There's always some internal impedance in terms of generation. How do you compensate for that? Well, you have a dynamic load. It is one of the experiments we do in the power engineering class. Trying to set up a dynamic load, vary the load, or vary the load impedance. So, get to a little bit more practical stuff here, problem solving. We look at one of the problems. So we have a 10-volt amplitude operating at 1,000 radians per second, and we can ask, what's the power produced and the power consumed in the circuit? Well, this becomes a phasor analysis problem. So very first thing we have to do is we have to find our impedances, of course. This is tan angle 0. Oops. Closing out my resistor, 2K, 1K, and again, my magic, minus J, 1K. So, how do we find the power in each component? You can do anything. How would we find the power for each component? Sure. So we can find the voltage here, call that VA. And what's VA? VA is, call that ZR1, just do things symbolically first, ZC. Well, that's ZR2 in parallel with ZC. ZR1 plus ZR2 in parallel with ZC. Do we agree? What's wrong? Oh, times V source. If we found, I didn't do it this way, so I don't have numbers for you, but if we found VA, what would we do next? And I'll do it the other way. What could we find quickly having found VA? So this is going to wind up being some phasor form, magnitude VA, angle VA, right? If we know VA, what do we know quickly? Well, VR2 and VC, right? So we could say power of R2 is what? Well, let's write it as complex. SR2, well, magnitude of VA, that's an amplitude. So magnitude VA squared over 2. And if we're going to use the voltage expression, times 1 over ZR2 conjugate. Well, what's ZR2 conjugate? Yeah, it's purely real. So this just winds up being magnitude VA squared, 1/2 out front, times R. So we use the phasor analysis to find the voltage at A, that's fine. Take the magnitude of that voltage at A, divide it by R, magnitude of that voltage at A squared. Real or imaginary? Plus J0. So if we go to our little table, I guess I called it R1 in the table. 1/2 VA squared over R1. What's this term? Resistors always have 0Q. Now on the same token, we can look at ZC, and that's 1,000 and that's 70. What's SC? Well, that's magnitude VA squared over 2, 1 over ZC conjugate. Well, what's ZC? Minus J1000. So what's ZC conjugate? J plus J1000. So we wind up with 0 plus magnitude VA squared over 2, 1 over J1000. That's ZC conjugate, which actually winds up being negative again. 1 over J is still minus J, that hasn't changed. And so we can go in our table and write minus 1/2 dA, I realize it's hard to read, all over 1,000. No J in there, it's just the Q. Q is always imaginary, it's implied. And what about our real part here? What's that going to be? So, 2 things to take away here. Resistive power. I realize what time it is. Always real. Q equals 0. Power greater than or equal to 0. Those are our 2 terms, the real component and the imaginary component. Reactive power. Always imaginary. So these are resistives, L and C. Q not equal to 0, but can be negative or positive. And power equals 0. No real power in inductors and capacitors. A parting shot. In real inductors and real capacitors, is there real power?
Yes.
Why?
Internal resistance.
There's always a little bit of internal resistance. Okay. We'll pick this up.